and improvise with time. So we just have a half an hour, and I'm just going to jump a little bit. But the key challenge and opportunity for us is to link connectivity, tractography, connectomics. What I try to teach you in my previous course is trying to make these things quantitative. For 20 years or so, these techniques were mostly qualitative. And people were just telling us, oh, you're just creating pretty pictures. Which was kind of true in a sense. Now we're trying to turn these pretty lines into quantities. And this is what I put on this side. This is what we're going to see this afternoon. But can we start getting access and at, axon diameter, myelin content, intracellular, extracellular water? So these terms are very hot topics. And I believe that to do these things well, you need the tracks. Just because if you understood my first hour and a half, we're measuring on the millimeter scale. We have 160,000 kilometers of axons. We don't have access to the individual axons. All we have access to is families of axons that traverse the same pixel, the same fiber element. And once we have a fiber element that comes from this side, this comes from tractography and connectivity, then we have access to, we go back to the data and we're like, okay, through this pixel, what is my myelin content? What is my axon diameter? And so I think this is the future. And this is what I'm trying to work a lot on in my lab, is to bridge the gap between microstructure and macrostructure and make connectivity quantitative. And what I'm not mentioning here, and you'll see at the end, is how do we bring this into multimodality, but true multimodality, where I have a vision one day that we will have PET data, so metabolism of tissue, function of tissue, structure of tissue, but not just axons, axon, myelin, vessels, astrocytes, oligodendrocytes. And I think diffusion and tractography could be the backbone computationally to integrate all these modalities together. So I love the next image, but this was an image in a review paper, which is, looking at the brain like a network of pipes of different sizes. In some pipes, you have water running. In other pipes, it's oil. In other pipe, it's gas. You have gray matter nucleus, gray matter cortex, white matter. And these pipes have features. And so you can draw this beyond white matter and include all the different building blocks of the central nervous system. And I think the backbone could be, white matter and how different cells arrange around it to connect the neurons together. And then I think my vision is that this is where the functional part comes in. But eventually we'll need to have these things dynamically imaged, right? And so it's not, that's what I mean when I say bring back the GPS into the pictures. Right now, I just have a static view of my roads and my orientations on the roads, but I don't have the traffic flow. I don't have the bus lanes, the walk, the piéton, what's a piéton in English? The pedestrian. Like, a pedestrian is not taking the main road, he's taking a sidewalk. And the traffic lights and the construction sites, and this is what we need to understand brain development, but also brain aging and brain diseases. So I'm just trying to bring a small brick into that problem. But I think as a community, and we're all computational people here, that if we work together towards a unified methodology, well, we can put all this together. And so a lot of what I'm presenting comes from this paper. It's actually a very short, interesting paper to read, even if you're not in the white matter world, but it was kind of a ha-ha moment for us in the community. It's like, okay, this is a hard problem, and we need to go at it together, because all we have are static images with orientations in them, and we're asking an algorithm to navigate through these orientations, and we think we're going to get anatomy from it. And what this paper says is like, this is difficult, and there's so many ways you can get lost or you can miss information. And basically there's a list of problems in there and challenges that I think is a recipe for, you know, tens of PhDs in the future. And so because of our grid, and that's exactly your question, Christophe, and because of the multiple potential of axons, geometry within a voxel, all these different ground truth geometries can lead to a crossing locally. But some are bendings that look like crossings. And so it's very hard if you don't have more than orientations to disentangle these configurations. It's impossible, actually. So either you have a very conservative algorithm, like DTI in a sense, that doesn't get lost, or you have a very aggressive algorithm, like probabilistic, that follows all potential paths and will find all potential connections and the combinatorial of it. So at the moment in the community, when we use probabilistic tractography, aggressive techniques, we're more on the side of we have too much in our tractogram, in our connectivity matrix. And there are techniques now that come afterwards to try to clean up, to try to filter the wrong tracks, to look at the problem more globally, inject some anatomical priors, look at the data, and try to remove the false positives that might have been created by following these local orientations. Yeah, because think of it. Imagine you're an algorithm starting from the motor cortex here, right? So you have maybe 100 voxels on the motor cortex. That's your initiation, and your target is the other hemisphere. Okay, 100 points. So all good. Jump on your car, get into the highway. Whoops, I got to cross the Champlain Bridge. And suddenly you're on a 3-lane highway. You started from 100 different cortical area. This is the mouth, this is the face, this is the leg. You're all going in, same 3 lanes. How do I go out here? Where do I go? It took us 20 years to figure that out. Come on, this was bound to fail. There's no way I can map end-to-end connection. Or I have to choose. Either I go from everywhere and I go out of here. It's like, take your bazooka, go everywhere. Okay, I can do that. Or take the most probable connection. Oh, okay, I'm going to end up here. I'm going to start from these 100 location and I'm going to finish here. That's what we're giving you. That's what it's in the tractogram. Now, that's what you have. If you press a button, you run TractoFlow or MRTrix. That's what's inside. So lots of work for my lab, but keep that in mind. It's wrong, doesn't mean it's useful, not useful. It can be useful, but it's limited. So what can we do? Lots of potential. And there's a whole list in that Nature Comp paper. More data, function, myelin, microstructure. We need to go beyond orientation, maybe anatomical priors, more anatomy, more priors. We've been dissecting brains for years. We know things that are connected and not connected. Let's inject that. Need more validation, need more data, need maybe AI, but it's like anything. We're going to need more data, more priors to find to help our algorithms be better. Not too depressed yet? No, but, and I always come back to my master's where I was segmenting images, and it was just after September 11th. And, you know, the biggest challenge was to find images of mustache and beard at the airport of bin Laden. 2001. Images of people at the airport of terrorists. We can do this on our cell phones today. Like, we couldn't handle glasses, nose, color of skin. This was 2021. My life was segmenting images. And we couldn't deal with a mustache in an image. It's true. We were so bad. We were detecting contours and gradients. We have sophisticated math to do geometry. But what did it take for us to break this problem? Examples, 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 ground truth examples, and not just AI. We had lots of better tools before deep learning revolutionized this problem, but I'm exaggerating, but we need that sort of revolution in tractography. And we're starting to do it. So I added these slides last minute because I want you guys to understand the talk this afternoon. This commit framework was invented by Alessandro Daducci. He visited my lab as a postdoc, but he really did that before he was in my lab. The idea is to try to bring back the data into the problem, the optimization problem of tractography. And so can we bring axon diameter, microstructure, to remove false positives that we create from tractography? And I'll just show you a slide that's going to help you understand this afternoon. I love this quote. This is from me, but there's no space for everyone. We cannot, in a sense, when we do tractography, I can track and just always find the same path without exploring the rest of the brain. If I'm always taking the same mistake, and I'm never actually getting this turn here, if I go back afterwards and I say, does my tractography explain the data? The answer is going to be no, because I'm going to have some missing space in the data. I need tracks and lines everywhere to explain the data. And not an infinite amount. If suddenly you give each pixel, each tract, an actual quantity, like a volume. So suddenly you have a forward model that says, okay, when I have a segment of tract traversing a pixel or voxel, there's water inside this tract that needs to explain the signal. Right? So you actually start tying together the microstructure model and the tractography. You say, okay, every tract globally, when it goes through a voxel, it has this amount of intracellular water, this amount of extracellular water, and the sum of these compartments needs to explain my diffusion signal. And you put this in a big convex optimization. So commit means convex optimization, microstructure. For microstructure, informed tractography. So the commit is the convex optimization part, and the MIT is the microstructure informed tractography. And just put that into an equation. So you have a data fidelity term. That's the way to go back to the diffusion data. And you also have, while you're at it, you can have the luxury to say, look, let's do what we know about the anatomy. Axons are not separate from the rest of the world. They come together. They come as a group. They come in fiber bundles. So I don't dive into the math here, but you can actually impose some sort of group sparsity on your data. You say, okay, I'm going to reconstruct the data with millions of tracks, but just pick the ones that explain the diffusion signal and that come in groups. so that suddenly you just get, but it's not perfect, but all the sort of mistakes that don't come in group, these guys say, I don't need them. I don't need this one to explain the data. I have all the other connections that come in groups. And what our friend is going to present this afternoon is you actually can go a step further here. You can complexify this and say, okay, not only does my track need to explain the diffusion data, but my track needs to explain the myelin data as well. So suddenly you go in at McGill in the group of Christine Tardif and Bruce Pike, and you say, oh, I'm going to do 10-minute high-quality diffusion MRI, and I'm going to add 10 minutes of quantitative myelin imaging. And that's a whole field, myelin water imaging or quantitative T1. But I'm going to use tractography to put them together. Because if they follow the same white matter, they need to explain the diffusion signal and the myelin. So why not put fMRI there as well? And so that's the future, in a sense, of putting the pipes, the white matter. And I'll show you videos later, but why don't I jump to that right away? So that suddenly, if you have false positives that are there, they're there in my data because I'm aggressively tracking the white matter. They're going to get removed. They're not supporting the data. They're not supporting the microstructure. They're not supporting the myelin. So they're going to get removed. And there's this actual very nice, so we were talking about validation, but I'll just jump to this image. But thanks to the challenge data and my work with neuroanatomists, we had found tracks that we always reconstruct that just don't exist. We know they don't exist. You start from the left hemisphere, you jump in the cortex, and you finish in the right motor cortex. This is always in your tractogram, always. It's always there. And 13,000 voxels, it's huge. And it's like Lego blocks. These damn traffic jams, it's as if you were not following your GPS. You go out of the Champlain Bridge on Descaries and you want to go to Toronto and you end up in downtown Montreal. But the roads exist. You're just getting lost there. You're taking a few bad decisions locally. And suddenly you run them through commit. So commit doesn't destroy your good tracks, those that don't exist, but suddenly, and that's important, look at the weight. The importance of these tracks, they're not fully zero, they haven't disappeared. So, but their weights are non-existent. And so that's what we recommend nowadays to put in connectomics, in that connectivity matrix. It's not track count, how many tracks are there in your connectome, but the commit weight, which is closer to the actual, and I'm going to big quotations here, connectivity strength. Strength in the sense that it explains the signal, it validates the priors, and yeah, so suddenly, if you have a raw tractogram with 90% density, right? It's the bazooka. I'm connecting everything to everything. So that's the reverse problems that I was discussing earlier with Obai, where the left hemisphere is not connected. This is the left and right hemisphere. You can see, like, we basically have a fully connected matrix here, basically 90% connected. You go through commit, and this is the commit weight. So a lot of zeros have appeared or very low commit weights, and suddenly this version is much cleaner and more quantitative. So that's the mini revolution in connectivity using tractography, is making tractography quantitative, and there's still room for improvement here. That's a big open question, by the way. I read a lot about this. Maybe Abib or some of you have answers for me, but what is the density of a brain? How heavily connected are we or not? So I read tons of papers on this, and it seems that just metabolically, to have a brain fully connected would just consume too much energy, too much glucose, and it would just be infeasible. Feels like between a third, around a third looks like the sweet spot in terms of brain metabolism, blood flow, perfusion, but I'm not an expert in that. But again, I'm just giving you ideas or intuitions where I think these communities should talk more. Because if I knew what is the ground truth density, it could help me tune my method as well. Because maybe I'm too aggressive here in the way I remove false positives or groups, right? There's a notion of scale here, of course. Questions? And so let me move to this part. So, yeah, I think I'm going to finish with this, but we see it well here. So for those that rarely see connectivity matrices, this is typically all the left hemisphere, all the right hemisphere. So you see how left hemisphere is very connected within the hemisphere, and these are the deep structures. The nucleus, thalamus, putamen, blah, blah, blah. And so this is an aggressive probabilistic tracking algorithm. You can see there's lots of connection before commit. And this is another graph, right, where all the left hemisphere, right hemisphere, and the different commissural connections. Yeah, and I usually show this graph. Now he left, but a lot of graph theorists are getting into this world of connectomics. It's a new field. Network neuroscience. And so how do we analyze these graphs? What are the right metrics on these graphs? How do we develop methods, machine learning, graph theory techniques on these graphs? So I'm not an expert in that, but you can imagine that now we just have another way to produce a graph. What I've been telling you all along is I think now I can produce a quantitative version of my connectome for all these modalities, right? I talked about diffusion, but now myelin, right? I could have the quantity of myelin between two pairs of connection. How does this myelin content change with disease, with multiple sclerosis? So myelin, lots of people working on quantitative T1, susceptibility weighted imaging, and angiography. What is the amount of vessels between two regions of the brain? Average size of vessels, average perfusion between two areas of the brain. I'm just trying to convince you that even though you're working on vessels or perfusion or metabolism or fMRI, I think we can try to put all this together, because this is just a little visualization, but you can see in red the segmentation of the vessels. And in color, it's my 50 different white matter tracks. And this is just qualitative, but you can imagine that you can start querying different regions of the brain, different functions, different white matter tracks with respect to their vasculature. And does disease change this vasculature? Does disease dilate vessels, contract vessels? So a big part of my lab also is in computer science. And so we try to push the visualization part of it, because these objects are heavy. They're more than just nifty images. And so putting them all together in a visualizing software is something we try to do. Lots of collaboration in Sherbrooke with PET. We are PET center in Sherbrooke. We can develop PET tracers of myelin activity, of glucose activity. And so when I talk about metabolism, you can easily imagine that if you solve the registration problem, and you can bring your PET data into tractography world, you can start wondering what is the metabolism of white matter. And that's also a very new field. Brain metabolism has been mostly looked at in the gray matter, where neurons live, but we have more and more tracers that are actually very sensitive in the white matter. So tau, for instance, in Alzheimer's disease is a protein in the white matter, and you can see tau progression in the white matter. And so that's what we've done with this group. So you have, for instance, in this project, a physical activity and a diet, a ketone diet. And in Sherbrooke, they created a ketones tracer. And so this is the image of the white matter before at baseline and then after. And you can see there's a huge ketone uptake everywhere in the white matter. This is not surprising. These people are not eating, they're just drinking ketones shakes. But you can actually start seeing how the brain uses ketones and where. And lastly, this project was done with Samuel Deslauriers. I know he presented here several times, but this is almost science fiction to me. And this is a simulation. Our dream would be to actually start mapping functional activity through the white matter. So we often see gray matter blobs correlated or activated or synchronized or desynchronized depending on your modality. But it'd be nice to visualize these synchrony or dyssynchrony in time through the white matter. And this, we need a little technology revolution, because just to solve a brain with 32 connections and 32 big areas was 2 to the 32 potential connections with fMRI activities of 1,000 time points. And so you can, without knowing a lot about this problem, you can imagine how heavy it is. And you have to bring this into even a forward problem or an inverse problem. But if I had to start a PhD again, I'd be there. And this is where I think also, yeah, lots of challenges. And so there's a new word that sometimes I use is chroniectomics. So the connectome is the static image. The chroniectomics is actually the connectome in time. And so, yeah, chroniectomics, the connectome in time, where we could follow brain activity, the dynamics of it, and eventually wonder how this changes myelin integrity, axon density, model disease progression dynamically. So yeah, little science fictions to finish. So yeah, it's about 12. And I think I've probably convinced you that your imaging modality of the future could actually be mapped into this world, where now I've zoomed in to the blood vessel, the stream, the astrocytes, the neuron, the axons, the myelin. But I can see one day where all these objects, all these modalities live in one sort of computational framework where we could play with all of them or some of them. So I'll break here. And I'm happy to take some question or discuss ideas.
Thank you very much. And maybe a few questions from the audience. Okay, let me start with, okay, go on.
Thanks a lot, Max, for the great talk. I was wondering to follow up on the last, of course, I'm aware of the work of Sam there. And if we follow what you said at the beginning, you said you need to extract a complex structure from, for the moment, just basic photograph, like of the road, for instance. Like you're not using time here. Or when you are using time here, you are using a very slow version of the time when you are using hemodynamic. But the direct version, if you take the idea, the direct version of the car running is actually coming from electrophysiology, from EEG and MEG.
Yeah.
So as opposed to do like here to go like inverse problem informed by the white matter, like should we try to use some information from electrophysiology to kind of like, as in your commit algorithm, try to find out what are the possible track? I think we should,
totally.
It would be probably possible to find like, I need that kind of propagation from there to there. So the possible track, because the other danger, I like that map a lot, but the other danger that we know is that this is not MEG activity along the track, because we are not measuring action potentials.
Right.
We are measuring.
It's just time delays.
Yeah.
Yeah. Totally agree. And in a sense, I didn't emphasize this, but the commit framework right now is limited because it's a filtering algorithm. You need the roads to start the process. And in a sense, if I was missing that U fiber in the beginning, there's no way for me to generate it except telling me that, you know, I badly explained my data. And so right now we're working hard on generative approaches that are in a commit-like framework, but generative to explain some data. If you were able to tell me what kind of electrophysiology data I can use to kind of help me guide the process, I think that would be amazing. And I didn't mention this. I had slides to tell you about reinforcement learning or learning-based algorithms, a bit like ChatGPT, able to predict the future of sentences based on prior data. But if somehow we have very controlled experiments in electrophysiology with known anatomy that we can use to kind of teach us about the dynamics and the anatomy underneath, that I think that could help us maybe disentangle areas where we don't know what to do. Very good point. Yeah. And I think we have the methods in place to start doing this.
Good. Any other question? No? Okay. I have one. You have not talked about, because when we look at the cortex, it has like a geometry, and this geometry is completely linked to the fibers. When we look at the curvature,
yes,
we know that the fibers are pushing there. So I know that this is something that you have included in your research program, but what about having this curvature like a kind of constraint or information about the number maybe of fibers or things like that?
Yeah, thanks, Habib. I didn't mention it. We talked with Ziki about it earlier, but Etienne Saint-Onge was actually a new prof at UCO, Université du Québec in Outaouais. So don't hesitate to reach out to him. He's building his activities and his new lab, but he's Mr. Cortex for us, where David Van Essen, who's at the origin of the model where he believes that cortical thickness is linked to the tension underneath, driven by fibers pulling as the brain develops from a flat surface to a folded surface. His theory is that fibers underneath pull as the brain develops. And this pulling, or the force of these pulling forces, is directly linked to the curvature of the surface and the thickness. And so we use some of these ideas to try to help tractography. And what Etienne now is trying to incorporate in his models is more notion about quantitative neurons and cortical thickness. But at the moment, we have a framework called surface enhanced tractography. And it's this notion that if you know the shape, see, of the cortex, you know it's normal. That's already a powerful information. And you can actually create a model of how axons should reach the deep white matter and how the deep white matter should project to the cortex. And the amount of axons also could be linked to cortical thickness. And so this was a first step of showing that if you do this, you can have much better connectivity. And that's something you've been using in your lab with Obai. And I don't know what the results are when you try to link this with functional contrasts. But in our world and the way we can evaluate test, retest, reproducibility, also the amount of cortex being reached by axons, this seems to be promising. Because that's another thing I didn't mention. But if you just take any random tool and run tractography, all the black areas of the cortex here are absent of tracks. You just don't reconstruct streamlines. So partly these U fiber problem, but also this fanning problem. And we tend to just hit the, what's it called? The crown of the bank, and not the bank and not the sulcus. And so we need to be better about shapes and geometry and also features of this cortex linked with tractography. So that's a big challenge still. And when you do use surface information, it's better, but it's not perfect still. I still have 30% of the cortex not covered with tracks. So it's okay if you have big blobs of fMRI or big parcels of free surfer, but as you zoom into micro connectivity or small parcels, V1, V2, smaller areas, I mean, this is an issue.
Another question is about this. The main things you show us is this connectivity. You follow the connectivity locally, and we would like to have this global view of the connectivity, because if you want to connect between the functional connectivity, which gives you the connectivity between population of neurons. So this is mostly global connectivity. We don't know the underlying link between the population of neurons. So if I want to merge between both of them, it seems to me that the tractography move locally and derive this local connectivity. We come with, at the end, with a global connection between areas, and the functional connectivity gives you the global connection. So can we simply use the functional connectivity to guide somehow some like tract that we are not sure that they exist between two population of neurons? Or so the way how I can introduce the function to guide the connection, or vice versa, this is something I think very interesting to do, how I can merge between the two.
And difficult. So I haven't followed a lot that literature, but from what I see, the challenge is if you have a functional link that's due to indirect anatomical connectivity. For instance, a passage through a nucleus. How do we handle this in tractography? Because if you tell me that these two areas are functionally connected, I'm going to search for a direct connection.
Yes.
Or I need a way to know that there's a potential indirect connection through a hub or something. So we need to introduce this kind of direct versus indirect connectivity.
Yeah, you're right. So because what we call right now functional connectivity is mostly in fMRI is correlation between areas, and we know that correlation between areas is not a direct link between two areas. It can be a completely indirect link. So we introduce for this purpose this partial correlation or conditional correlation to look at the more direct relationship between two areas. Maybe this is more helpful to look at the direct link.
That would be nice to revisit. And also I was going to say graph-based techniques were introduced in the early 2000s and left aside for about 20 years because we just didn't have the computational power to handle graphs properly. But I can feel that they're coming back in the tractography world. But once you have a graph, and this graph can support both direct and indirect connections, I think then you can potentially explore many local minima or many solutions of your problem. That commit gives you just one, but in a sense, you need more than one. So
my last question is, let's say you have the model of the capillaries, because you can get this information from sequence of fMRI, so you can have the vasculature of the brain. You can have also the information about the, let's say, the other cells, oligodendrocyte or astrocyte, and but I have not seen how you can bring this model in the anatomical connectivity, framework, because this is mostly function, so metabolism. So how you try to merge between
the only thing we show right now, we show it, we visualize it. So if you can reconstruct a feature and you can turn into a voxel float or a number, we can show it on the white matter graph in a sense. So it's a visualization support at the moment. We don't have the methods, the models to incorporate them together. Having said this, right now in the diffusion world, it's all about the gray matter and gray matter diffusion. And they're starting to include more than just neurons in the Ford model. So what I tell people then is always show me, it's like in my first lecture, is show me how it looks under the microscope. And then let's throw in little water molecules and let's try to understand what would an astrocyte or an oligodendrocyte create in terms of obstacle on the water molecule. And if we can answer this question and model it, we can write it in an equation and try to infer it from the data. So that's kind of the game we have to play. It's like, can we draw it? Can we see it on the microscope and add the different cells? And then simulate a finite element random walk and see how that would lead to a signal in diffusion. And then go to the data and say, can we inverse it? Mm-hmm. That would be my kind of attempt and say, okay. And nowadays we can deal with blood vessels, axons and myelin, but nothing else. Mm-hmm. Anything else outside these structures is empty space or free space, but it's not free space. So let's start complexifying that free space, and then we can just, I think we can start building the Lego blocks. Mm-hmm. And we're gonna need more than a pixel.
Yes.
The fiber element now is gonna improve, but it's true, the fiber element will explode in multiple sub-elements.
Absolutely. I 100% agree with this idea. Last question is about the, we talk about the diffusion within the fibers.
Yeah.
Okay, that's fine. If we look at the whole model proposed in the literature, this diffusion is linear diffusion, usually.
Yes.
But if I look to the geometry of the fibers, there is a microtubule within the fibers, and the water molecule is moving around the microtubule, and probably not at the same speed. So even at the level of the fibers, the diffusion becomes somehow like a nonlinear diffusion within the fibers.
Yeah.
Have you think about this kind of problem and how you can introduce?
Not me, but a theoretical physicist has done it. not done it. He's not done, but it's Dmitry Novikov at NYU. You should look at his work. He has a few nice high impact papers, but his proposition is the standard model, but he introduces time in the diffusion process. And so now for him, diffusion should not be just static. And I didn't mention about the physics, but you might have heard about the B value in diffusion. The B value is a way to encapsulate time. So he's a big fan of multi-B value images, and he thinks that in these multi-B value images, you have some knowledge to start disentangling the nonlinear speed of water molecules within structures. It's
interesting.
It's interesting. Yeah.
Okay, thank you. Any other question from the audience?
Cool.
Okay, cool. Everything is clear. That's what it means. Okay, so thank you very much, Maxime, for this very nice presentation. So the lecture and the research program and this overview about the diffusion imaging. I think we almost the time when I listen to your talk, I learned something. So it's really something that I appreciate. So thank you very much, and
That's it.
so let's